Hello and welcome to 12-3 Part 1. Today we are discussing tangent lines. Now the first few slides of this is not stuff that you're writing. It's already written for you in your notes. I just want to discuss it. Calculus is a branch of mathematics that studies rates of change in functions. In fact, in 12-4 we're going to get into something called the derivative, which is basically the instantaneous rate of change, or the instant rate of change. To determine the rate at which a graph rises or falls at any individual point, you find the slope of the tangent line at that point. In the simplest terms, the tangent line to the graph of function f at some point where point P is x comma y is the line that approximates the slope of the graph at that point. So some examples of tangent lines. Notice here how you have this curved graph. Let me get out my laser pointer. Okay, notice here I've got this curved graph. I have point P. In this case, I care about the line that is tangent. It intersects this point at exactly one spot. It hits it, and it's perfectly tangent. Same thing over here on this sort of curve right here. Could be an exponential, could be part of a hyperbola. Okay, this curve right here, notice how at point P you have this line that's going to barely touch it. Over here with this parabola, it just happens to be down here at the minimum, this tangent line at point P. Remember from geometry that a tangent line is a line that touches a circle or a curved object at exactly and only one point. So tangent lines to non-circular graphs can intersect at more than one point. Obviously, in the first example I gave you back here, if this line were extended, it would intersect it at more than one point. But at the specific reference point, we want the slope or the equation or the slope of the line that is tangent to the function at that point. Because the tangent line approximates the slope of the graph at that point, the problem of finding the slope of the graph is the same as finding the slope of the tangent line at that point. So for example, use the graph in the figure I'm about to show you to approximate the slope of the graph f of x equals x squared at the point 1, 1. So from the graph of f of x equals x squared, you can see that the tangent line at 1, 1 rises approximately 2 units for each change in x. Okay, feel free to take out a graphing calculator and plug in y equals x squared. So you can estimate the slope of the tangent line at 1, 1 to be the slope is the change in y over the change in x, or it's rising 2 over 1. So therefore you can say that the tangent line has a slope of about 2 at that point. Here I give you an example of another parabola. This figure shows the normal monthly temperatures in degrees of Fahrenheit for Dallas, Texas. Approximate the slope of this graph and the indicated point and give a physical interpretation of the result. So notice here on the right, I've got the parabola, the distribution of data drawn in here, and I've got at that point 10, 69. So in January, I'm sorry, not January, month 10 is October, not January. It's approximately 69 degrees is what we expect. At that point, if I were to draw a line that just hits the graph at exactly that one point, the slope of that graph, if I were to manually calculate it, just by counting boom, 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 is up 16 over 2. So you basically have a negative 8 degrees per month. So your change in y was negative 16. If you were to follow this graph, this is a negative slope. It goes from here, goes to the right 2, or the change in x is positive 2, and then down 16 for the change in y. So it's 8 degrees per month at that point. That is the tangent line. Now, to find it algebraically, the slope of the graph f at the point of x comma f of x, or x comma y, is equal to the slope of its tangent line at that same point, and it is given by the following limit. That the slope of the tangent line is equal to the limit as h approaches 0 of the slope of the secant, or the limit as h approaches 0 of f of x plus h minus f of x over h. What's going to end up happening here is that if you have a graph, if you have some sort of function, f of x, you're going to end up plugging in for f of x, x plus h. So if it was, x plus 1, you'd have x plus h plus 1 minus x plus 1 over h. Let me show you an example. So find the slope of x squared at the point negative 2 comma 4. So the first thing I'm going to do is set up my difference quotient, which is basically I'm going to plug in for x, negative 2 is what I'm going to plug in for x. Remember, according to this right here, I'm having x plus h minus f of x over h. Meaning that for this portion right here, let me get out I want to draw with a pen for you here. Okay, for this portion right here, I am plugging into my function this term, x plus h. Okay? If they give me what x is at the point, if they tell me the point on the graph is 2 comma 1, then 2 goes here for x. Okay? If they don't tell that to me, then I just leave it as x, and I leave h alone, and then I subtract, and then right here, I'm just simply plugging in x into the equation and solving it. Okay? So in this case, this portion right here, negative 2, came from negative 2 up here. So my different quotient is going to basically take the formula I had on the last page, and for anywhere I have my x, I plug in my negative 2. Now I'm going to take this function notation, and I'm going to change this and this to look like this. So f of x equals x squared. So since I'm plugging negative 2 plus h in for x squared, I square it. And then I subtract f of negative 2, which means I plug negative 2 into that equation and have negative 2 squared. Now I just simply do some math. I expand my terms, in which case this right here would become negative 2 plus h times negative 2 plus h. So what happens is I'm basically going to FOIL it. My first are 4, my outer minus h, minus 2h, my inner minus 2h, and my last h squared. So I end up getting that right there of 4 minus 4h plus h squared. Next, I simply take negative 2 and square it to get 4. My 4 and negative 4 are eliminated, so I simplify to get negative 4h plus h squared over h. I can factor out an h and divide it out, and I would have to do that because if I tried to take the limit as h approaches 0 of that equation, I would get something that's undefined because I have an h in the denominator. Now that those have been eliminated, I have negative 4 plus h. I plug in 0 there, and I get negative 4 as my answer. So the slope of the tangent line at f of x equals x squared at the point negative 2 comma 4 is, or negative 2, 4 is negative 4. Find the slope of negative 2x plus 4. F of x equals negative 2x plus 4. I'm going to use my difference quotient. Okay. Now notice what I've done here is I'm plugging because I have not been given any point. My point here is just simply x, comma, y. I haven't been given an x or y. So since I've got x comma y as my point, now inside of this equation for x, I'm going to plug x plus h in. So right here, I'm plugging this term in for x, which brings me to right here. So I've got negative 2 times x plus h plus 4, and then I do my second half of it, which is f of x, which is just simply a rewriting of this to right there. Now, I don't have to plug anything in because they did not give me a specific point in which to evaluate it. Okay? So now, I have, of course, h in the denominator. I simplify. I have minus 2x plus 2x. That goes away. 4 and negative 4, they go away. So these are eliminated. Those are eliminated. I'm left with negative 2h over h divided out, and it's just simply negative 2. Now that makes sense because they told me to find the slope of a line, and I know from Algebra 1 that it's simply the coefficient in front of x. So now you're thinking, did we really have to do all that work when we could have just circled it in the first place? Yes, because we used a difference quotient. Remember, with the difference quotient, what you're doing in this case is you're plugging in x plus h into x, and then you're subtracting it by the function. That's why they call it a difference quotient, because you're adding in an h, so it's x plus h, and you're plugging it in for x, and then you subtract it by f of x and divide by h.